Okay, so far we've established the relationships of observable space, and we've established the relationships that occur within unobserved space. And when we combine these two together, we get a perspective in unified space. And there's when we describe these relationships, we can look at this as an eye of God perspective, and then eventually we'll also convert this to what our local perspective would be on cosmological type of events. And now there's this kind of notation that I use to kind of make it a little bit easier to describe these things and when you see the relationships. But basically, relationships established in relative space, which are basically local measurements, are all lowercase letters. The absolute observable space relationships are done in capital letters. Then, and I don't know if many of you noticed, but when we did the absolute relationships of unobserved space, I did it in italic and capital letters. And then when we unite these things together, unified cosmological absolute perspective, where we unite the unobserved and observable space together, I did that in capital bold letters. We see, and then when we do it a unified cosmological local perspective, the notation that was used is large, bold, lowercase letters. Now, the first thing that's kind of like important to kind of add the relationships in unified space for, or they're considered here, are those we would see in or what I call orbital relationships. Now, orbital relationships in general are just basically any dynamic system where there's a balance between spatial type forces with inertial forces, resonant circuits, and so forth. Okay, so when I say orbital relationships, we're actually looking in general a dynamically resonant system. And the first one that to deal with was how would orbital relationships as observed, let's say, within an atom or objects rotating in space, how would these vary? And so from observable space, we had the proportional change in the radius varied over the 2/3 power of the absolute ratio. And then when we consider the effects of unobserved space, which is primarily due to the loss of inertia, that the radius would vary to the 1/3 power. Well, when you integrate these two together, the radius of an orbit would vary to the t to the 1/3. The radial measure associated with observable space is more powerful than is the effect of the loss of inertia. So overall, the radial orbits would be smaller in the past, but increasing over time. And similarly, we do the same thing for the velocity within an orbit, and we have the absolute ratio of how the velocity would vary in observable space, and then we have unobserved space, how the velocities of orbits would change. When we integrate the two together, we have the final, and it's interesting that the velocity from associated with orbits would be constant. There would be, in essence, no change. When you add the effects of observable space and unobserved space, the orbital relationships, the velocity in orbital relationships, basically they maintain a constant, which is kind of interesting to find that out. And then we can also do the same thing for discovering what the relationship of acceleration is, and one simple way is just v squared over r. And when we go through a relationship, that the acceleration should vary to the 1/3 power. Now, intervals of time, which are this will be finally, we'll see intervals of time actually kind of appear, which is going to be important because it helps establish a dilation effect. But intervals of time are distance divided by the velocity, so we add these relationships for orbital relationships in unified space. We get that the periods of orbits or dynamic systems would vary to the 1/3 power. And then we also have the repeating here the same thing with spatial inertial masses, that the spatial mass would remain constant and inertial mass is varying over the course of cosmological periods of time. And then there's some checks here for dimensional consistency, make sure it's consistent. Now, this next part of this discussion